The National Electrical Code, specifically Section 250.56b, addresses the testing of grounding electrodes. This section outlines the requirements for verifying that the soil or other material in contact with the grounding electrode has a resistance to ground of 25 ohms or less. The code mandates that this test be conducted both before the electrode is installed and after installation, but prior to making any system grounding connections. The process involves measuring the resistance from the grounding electrode to a reliable ground reference. A suitable ground reference can be another grounding electrode driven at least 6 feet, which is equivalent to 1.83 meters, into permanently moist earth. It is critical to understand that the resistance of the grounding path or the grounding electrode itself must not exceed 25 ohms. To ensure accurate and representative measurements, it is recommended to conduct the test during the driest time of the year, particularly in dry climates. Artificially altering the soil conditions by emptying wells or wetting the area around the grounding rod is not an acceptable practice. There are various testing methods available to measure soil resistivity. One of the most commonly used techniques is the fall of potential test. A detailed explanation of this test can be found in IEE Standard 81-1983 titled IEE Guide for Measuring Earth Resistivity, Ground Impedance, and Earth Surface Potentials of a Ground System. The fall of potential test involves injecting a test current into the earth through an auxiliary electrode and measuring the resulting voltage drop between the grounding electrode under test and another auxiliary electrode. By carefully analyzing the voltage and current measurements, the resistance to ground can be determined. Understanding the principles behind grounding and bonding is crucial for electrical safety. A properly grounded system provides a lower impedance path for fault currents, helping to quickly trip circuit breakers or fuses and minimize the risk of electrical shock. The 25 ohms resistance requirement is intended to ensure that the grounding electrode is effective in providing this low impedance path. It is important to note that the NEC provides minimum requirements, and in some cases, achieving a resistance of 25 ohms or less may be challenging. In such situations, additional grounding electrodes may be required to improve the overall grounding system performance. Factors such as soil type, moisture content, and electrode depth can all affect the resistance to ground. Consulting with a qualified electrical engineer or grounding specialist can help ensure that the grounding system is properly designed and installed to meet the specific needs of the installation. The fall of potential test is one method to measure earth resistance. Here is a breakdown of the process. Firstly, disconnect the grounding electrode conductor from the grounding electrode to isolate the electrode under test. Secondly, drive 2 auxiliary ground rods into the earth in a line away from the grounding electrode. The auxiliary electrodes should be spaced at least 20 feet apart, and the distance from the grounding electrode to the nearest auxiliary electrode should also be at least 20 feet. Thirdly, connect a ground resistance meter to the grounding electrode and the 2 auxiliary electrodes. The meter will inject a test current into the earth and measure the voltage drop between the grounding electrode and the first auxiliary electrode. Fourthly, calculate the resistance by dividing the voltage drop by the test current. This resistance value represents the resistance of the earth between the grounding electrode and the first auxiliary electrode. Fifthly, move the first auxiliary electrode to different locations along the line between the grounding electrode and the second auxiliary electrode. At each location, measure the resistance and record the value. Sixthly, plot the resistance values versus the distance from the grounding electrode. The resulting curve should have a flat portion, which represents the true resistance to ground of the grounding electrode. The point where the curve flattens out is the most accurate measurement of the earth resistance. If the curve does not flatten out, it may be necessary to increase the distance between the auxiliary electrodes or to use a different testing method. The 25 ohms requirement outlined in NEC 250.56b is a crucial safety measure that helps to protect people and equipment from electrical hazards. It is essential to understand the testing procedures and to ensure that the grounding system meets the minimum requirements of the code. The purpose of a grounding electrode system is to provide a low impedance path to earth for fault currents. This allows overcurrent protective devices such as circuit breakers and fuses to quickly trip and clear the fault, preventing electrical shock and equipment damage. When a fault occurs in an electrical system, such as a short circuit, a large amount of current can flow through unintended paths. If the grounding system is not properly designed and installed, this fault current can flow through people or equipment, causing serious injury or damage. A properly grounded system provides a safe path for the fault current to flow back to the source, allowing the overcurrent protective device to quickly interrupt the circuit. The grounding electrode system typically consists of one or more grounding electrodes, such as ground rods, ground plates, or underground metal water pipes, that are connected to the electrical system. The grounding electrodes are buried in the earth and provide a low-resistance connection to the ground. The size and type of grounding electrode required depend on the size of the electrical system and the soil conditions. The NEC provides detailed requirements for the selection and installation of grounding electrodes. In addition to the grounding electrode system, the NEC also requires that all metal enclosures and equipment be bonded together to create a low impedance path for fault currents. Bonding is the process of connecting metal parts together to ensure that they are at the same electrical potential. This helps to prevent voltage differences between metal parts, which can cause electrical shock. The bonding system typically consists of bonding conductors, such as wires or straps, that connect metal enclosures, equipment, and other metal parts together. The size and type of bonding conductor required depend on the size of the electrical system, on the amount of current that could flow through the bonding conductor during a fault. The NEC provides detailed requirements for the selection and installation of bonding conductors. The grounding and bonding systems work together to provide a safe and effective path for fault currents. The grounding electrode system provides a low impedance connection to earth, while the bonding system ensures that all metal parts are at the same electrical potential. By properly grounding and bonding the electrical system, the risk of electrical shock and equipment damage can be significantly reduced. Here are some additional considerations regarding grounding electrode testing. Firstly, multiple electrodes. If a single grounding electrode does not meet the 25 ohms resistance requirement, the NEC allows for the installation of additional grounding electrodes. These electrodes should be spaced at least 6 feet apart and connected together to form a grounding electrode system. The combined resistance of the grounding electrode system should be 25 ohms or less. Secondly, concrete encased electrodes. A concrete encased electrode, also known as a UFO ground, is a grounding electrode that is encased in concrete. This type of electrode is often used in new construction and can provide a very low resistance to ground. The concrete encased electrode must be at least 20 feet long and must be encased in at least 2 inches of concrete. Thirdly, metal underground water pipe. A metal underground water pipe can be used as a grounding electrode if it is in direct contact with the earth for at least 10 feet. The water pipe must be electrically continuous and must not have any insulating joints or coatings. Fourthly, engineered grounding systems. In some cases, it may be necessary to use an engineered grounding system to achieve the required resistance to ground. Engineered grounding systems are designed by qualified electrical engineers and typically involve the use of specialized grounding electrodes and soil treatment techniques. It's important to note that electrical codes and standards are subject to change. Always consult the latest edition of the NEC and any applicable local codes for the most up-to-date requirements. If you are unsure about any aspect of grounding electrode testing or the design of a grounding system, it is always best to consult with a qualified electrical professional. Grounding and bonding are critical components of electrical safety, and it is essential to ensure that these systems are properly designed and installed. In addition to the information provided in the NEC and IEEE standards, there are many other resources available to help you learn more about grounding and bonding. These resources include textbooks, online courses, and training programs. By taking the time to educate yourself about grounding and bonding, you can help to ensure the safety of yourself and others. Here are some common grounding electrode types. Firstly, ground rods. These are typically copper or copper-clad steel rods driven into the earth. They are a common and relatively inexpensive grounding solution. Secondly, ground plates. These are metal plates buried in the earth. They offer a larger surface area than ground rods and can be more effective in areas with poor soil conductivity. Thirdly, underground metal water pipes. As mentioned earlier, these can be used as grounding electrodes under certain conditions. However, their suitability depends on the type of metal, the length of underground contact, and the presence of any insulating joints. Fourthly, concrete encased electrodes. These are reinforcing bars or bare copper conductors encased in concrete foundations or footings. They provide excellent grounding due to the large surface area in contact with the earth. Fifthly, ring grounds. These are bare copper conductors buried in a loop around a building or structure. They provide a comprehensive grounding system and are often used in areas with high lightning activity. Choosing the right type of grounding electrode depends on several factors, including soil conditions, the size of the electrical system, and local code requirements. It's important to consult with a qualified electrical professional to determine the best grounding solution for your specific application. Furthermore, the fall of potential test, while widely used, may not be suitable in all situations. In areas with limited space or high levels of electrical noise, alternative testing methods may be necessary. One alternative method is the slope method, which involves taking resistance measurements at multiple distances from the grounding electrode and analyzing the slope of the resulting curve. Another alternative method is the stakeless method, which uses specialized clamps to measure the resistance of the grounding electrode without the need for auxiliary electrodes. These alternative methods can be more convenient and accurate in certain situations, but they require specialized equipment and expertise. Therefore, understanding the limitations of each testing method is important, and selecting the appropriate method for the specific application is crucial. Also consider soil resistivity, which varies significantly depending on factors such as soil type, moisture content, temperature, and mineral content. Sandy soils typically have higher resistivity than clay soils, and dry soils have higher resistivity than moist soils. Soil resistivity can also vary with depth, with deeper layers often having lower resistivity due to higher moisture content. Measuring soil resistivity is an important step in designing a grounding system. The most common method for measuring soil resistivity is the Wenner 4-point method, which involves driving 4 electrodes into the earth in a straight line and measuring the resistance between them. The spacing between the electrodes is varied to measure the resistivity at different depths. The soil resistivity data is then used to calculate the required length and number of grounding electrodes. Understanding the concepts of impedance and reactance is crucial when evaluating grounding systems. While resistance is a measure of the opposition to current flow in a direct current DC circuit, impedance is the total opposition to current flow in an alternating current AC circuit. Impedance includes both resistance and reactance. Reactance is the opposition to current flow caused by capacitance and inductance in an AC circuit. Grounding systems should have lower impedance to ensure that fault currents can flow quickly and safely back to the source. High impedance can impede the flow of fault currents, increasing the risk of electrical shock and equipment damage. Measuring impedance requires specialized equipment and techniques. A ground impedance tester is used to inject a test current into the grounding system and measure the resulting voltage drop. The impedance is then calculated by dividing the voltage drop by the test current. Regular inspections and maintenance of grounding systems are essential to ensure their continued effectiveness. Grounding electrodes should be inspected periodically for corrosion and damage. Connections should be checked to ensure that they are tight and free of corrosion. The resistance to ground should be measured regularly to verify that it is still within acceptable limits. Any problems with the grounding system should be corrected promptly to prevent electrical hazards. Furthermore, lightning protection systems are closely related to grounding systems. Lightning protection systems are designed to protect buildings and structures from damage caused by lightning strikes. A lightning protection system typically consists of air terminals, down conductors, and a grounding system. The air terminals are installed in the roof of the building and are designed to intercept lightning strikes. The down conductors are heavy gauge wires that connect the air terminals to the grounding system. The grounding system provides a low impedance path for the lightning current to flow to earth, preventing damage to the building and its contents. The grounding system for a lightning protection system should be designed and installed in accordance with the requirements of NFPA 780 standard for the installation of lightning protection systems. The grounding system should have a low resistance to ground to effectively dissipate the lightning current. Surge protection devices, SPDs, are another important component of electrical safety. SPD are designed to protect electronic equipment from damage caused by voltage surges. Voltage surges can be caused by lightning strikes, power grid switching, and other events. SPD work by diverting the surge current to ground, preventing it from reaching the protected equipment. SPD should be installed at the service entrance and at sensitive electronic equipment. SPD are rated by their surge current capacity, which is the maximum amount of current that they can safely divert to ground. The surge current capacity should be selected based on the expected surge levels in the area. It is critical to understand the difference between equipment grounding and system grounding. Equipment grounding is the connection of non-current carrying metal parts of equipment to ground. This provides a low impedance path for fault currents, allowing overcurrent protected devices to quickly trip and clear the fault. System grounding is the connection of the neutral point of an electrical system to ground. This helps to stabilize the system voltage and provides a reference point for fault detection. Both equipment grounding and system grounding are essential for electrical safety. In addition to the NEC, there are other standards and organizations that provide guidance on grounding and bonding. IEE, the Institute of Electrical and Electronics Engineers, publishes several standards related to grounding and bonding, including IEE Standard 142, Recommended Practice for Grounding of Industrial and Commercial Power Systems, also known as the Green Book. All Underwriters Laboratories lists and certifies grounding and bonding equipment. NEC, the International Electrical Testing Association, provides certification for electrical testing personnel. Familiarizing yourself with these standards and organizations can help you stay up to date on the latest grounding and bonding practices. And remember that working with electricity can be dangerous. Always follow safe work practices and wear appropriate personal protective equipment (PPE) when working on electrical systems. If you are not qualified to work on electrical systems, hire a licensed electrician. Safety should always be your top priority. When performing grounding electrode testing, it's crucial to be aware of the potential for step and touch potential hazards. Step potential is the voltage difference between 2 points on the ground that a person could step between. Touch potential is the voltage difference between a grounded object and the point on the ground where a person is standing. High step and touch potentials can occur near grounding electrodes during fault conditions or lightning strikes. To minimize the risk of step and touch potential hazards, keep a safe distance from grounding electrodes during testing. Wear rubber-soled shoes and avoid touching grounded objects while standing on the ground. If possible, perform the test from a remote location. In areas with high levels of electrical noise, it may be necessary to use shielded test leads to reduce interference. Electrical noise can distort the test results and make it difficult to obtain accurate measurements. Shielded test leads help to block out electrical noise, ensuring that the test measurements are accurate. When selecting a ground resistance meter, choose a meter that is appropriate for the type of testing that you will be performing. Some meters are designed for testing small grounding systems, while others are designed for testing large grounding systems. Make sure that the meter has the appropriate range and accuracy for your application. Before using a ground resistance meter, always calibrate it according to the manufacturer's instructions. Calibration ensures that the meter is providing accurate readings. Regular calibration is essential to maintain the accuracy of the meter over time. When installing grounding electrodes, make sure that they are installed deep enough to reach moist soil. The depth of the grounding electrode will depend on the soil conditions in your area. In general, grounding electrodes should be installed at least 8 feet deep. Follow local electrical codes and regulations for grounding electrode installation requirements. Local codes may have specific requirements for the type, size, and depth of grounding electrodes. It is important to comply with all applicable codes and regulations to ensure the safety of the electrical system. Keep accurate records of all grounding electrode testing and maintenance. These records should include the date of the test results, and any corrective actions that were taken. Maintaining accurate records is essential for tracking the performance of the grounding system over time. It is also helpful for troubleshooting problems with the grounding system. Consider using grounding-enhancing compounds in areas with poor soil conductivity. Grounding-enhancing compounds are materials that are designed to improve the conductivity of the soil around grounding electrodes. These compounds can help to reduce the resistance to ground, especially in areas with sandy or rocky soils. When using grounding-enhancing compounds, follow the manufacturer's instructions carefully. These compounds can be corrosive and may require special handling. Consider using exothermic welding to connect grounding conductors. Exothermic welding is a process that uses a chemical reaction to create a permanent, low-resistance connection between grounding conductors. Exothermic welds are stronger and more corrosion-resistant than mechanical connections. Exothermic welding should be performed by qualified personnel who are trained in the proper techniques. In some cases, it may be necessary to use a combination of grounding electrodes to achieve the required resistance to ground. For example, you might use a ground rod in combination with a ground plate or a concrete-encased electrode. Combining different types of grounding electrodes can provide a more effective grounding system. Remember that grounding is not a substitute for overcurrent protection. Grounding provides a path for fault currents to flow back to the source, allowing overcurrent protective devices to trip and clear the fault. However, grounding does not prevent faults from occurring in the first place. Overcurrent protective devices, such as circuit breakers and fuses, are essential for protecting electrical systems from damage caused by overloads and short circuits. If you are unsure about any aspect of grounding or bonding, consult with a qualified electrical engineer or grounding specialist. Grounding and bonding are complex subjects, and it is important to get expert advice if you have any questions or concerns. A qualified electrical engineer or grounding specialist can help you design and install a grounding system that meets the specific needs of your application. In addition to the technical aspects of grounding, it is also important to consider the legal and liability aspects. If someone is injured or property is damaged as a result of a faulty grounding system, you could be held liable. Make sure that your grounding system is designed and installed in accordance with all applicable codes and standards to minimize your liability. Review relevant case studies and lessons learned from past grounding failures. Analyzing past grounding failures can help you identify potential problems with your own grounding system and take steps to prevent similar failures. There are many resources available online and in print that provide case studies and lessons learned from grounding failures. By studying these resources, you can gain valuable insights into the importance of proper grounding. Stay informed about new technologies and advancements in grounding and bonding. The field of grounding and bonding is constantly evolving, with new technologies and techniques being developed all the time. Stay informed about these advancements by attending industry conferences, reading trade publications, and participating in online forums. By staying up to date on the latest technologies, you can ensure that your grounding system is using the most effective and efficient methods available. Finally, promote a culture of safety and awareness regarding grounding and bonding. Make sure that everyone who works with electrical systems understands the importance of grounding and bonding and the potential hazards associated with improper grounding. Encourage employees to report any concerns about the grounding system and take prompt action to correct any problems. By promoting a culture of safety and awareness, you can help to prevent electrical accidents and injuries.